Okay, let's get started. So last week we talked about some network basics. We talked about what are network hosts, what are communication mediums, and some protocols. So we mentioned a little bit about the OSI model. So we will start from here today. So OSI stands for the Open System Interconnection. This model, the OSI model, was actually developed in 1984. It's like many, many years ago. So by this international organization for the ISO anyway. So this model actually only defines what is needed to be done to send the data from one computer, one host to another. And it doesn't define how we are going to do it. So the OSI model is, we saw the figure last Friday. It's a 7-layer theoretical and a very fine-grained model that helps us to understand how we can transfer data from one user, one computer to another. And it has been the model that helps us develop all kinds of standards so all our hardware and software can talk with each other. So we took a look at this last Friday. So there are 7 layers: physical layer, data link, network, transport, session, presentation, and application. And this is very fine-grained, very detailed. So when people actually develop network architecture, they find that sometimes we don't need some of those layers. So I will give more detailed example in a moment. So, but still, let's try to understand each model, how it works, what it is for. So let's use this post office analogy here. So if you write a letter, 20-page letter to a foreign country, so you are the application, and this is the application layer data. And this data is translated to another language, so the destination, the recipient, can understand it. And this is in the presentation layer. And after that, the session layer ensures that the intended recipient can really receive this letter by creating a session. It's a dynamic session. Then the transport layer will try to separate and number pages so they can send the pages one by one. Well, in a postal example, you don't really send the pages one by one, but you can do that. So like a registered mail, this transport layer can track delivery and request another package if one package is lost. For example, if one page was lost, the recipient doesn't get it, the recipient can ask for, could you please send that page again? And the network layer is like the postal center, or there are maybe several postal centers. They sort the letters by zip code and route them closer to the destination, which means route them to the local post office. And the data link layer, this is what we're going to talk about today. The data link layer is like a local post office. You can give the letter you want to send to the local post office, and the local post office will be the office that actually send you the letter if you are the recipient. So the local post office will decide use what vehicle to deliver these letters. And the physical layer is like the trucks, the planes, those vehicles that actually carries that letter. So it could be between postal centers, it could be between a local office to a postal center. So after this, today we are going to look at the TCP/IP suite. So we are going to talk a little bit of the TCP/IP suite history, compare the TCP/IP model with the OSI model, and we were introduced a concept of protocol data unit. You will know what it is in a moment. So we discussed this a little bit last week. So in 1969, maybe 1 or 2 years after DARPA initiated this ARPANet object, there were only 4 or 5 hosts. So they are actually just several computers on each site, and there is no network of network. At that time, the ARPANet was just a network of computers, network of hosts. So right now, the internet is network of network. That's a major difference. So because they are the same, they are the host on the same network, they have to use the same physical layer. They have to use the same physical communication channel. Otherwise, they cannot be collected. So even though those hosts were scattered at several universities, even BDNs, the military contractor, but they act like a scattered local area network. Then DARPA realized this is a huge problem. We cannot make this scalable. So they wanted to collect many separate, dissimilar, which means using different physical devices as a layer to create an inter-network. So they started another project, and in 1974, Wendt and his co-author published this paper in IEEE Transactions on Communication. The paper is titled "A Protocol for Package Network Intercommunication." And this is a paper that the first time proposed TCP. And this is actually a figure in the original paper. So at that time, the protocol is not called TCP/IP. It just is a TCP. And 3 years later, they did a demo. And the first time they were able to collect 3 different networks: the ARPANet, the SATnet, and a package radio network. So you can see those 3 networks, at the data link layer, they use different physical networking devices actually. So in 1978, they split the TCP protocol to TCP and IP because that they find out sometimes they don't need the reliability guarantees offered by TCP. They just want faster transportation. So by separating this TCP and IP, they will be able to build another protocol, UDP, on top of IP. And we saw the next big milestone was 1984. All the 1,000 hosts, they converted to TCP/IP. And right now, TCP/IP is the most widely used network protocol architecture. So everyone, you are using a phone, you are using a laptop, you are using this TCP/IP. And our internet is using this, our web is using this. So TCP/IP suite is not the only attempt to achieve internetworking. There were other attempts too. For example, IBM in 1974, they have a system called System Network Architecture. Also, DEC, they have this DECnet. And there are other standards. But there is one very interesting, it's called IPX and SPX. IPX resembles IP, and SPX resembles TCP. So if you ever play the video game Red Alert 2, like I did, you should be very familiar with this IPX and the SPX. So this game was released like, I don't know, 2001 maybe, 15 years ago. And if you want to play Red Alert with your friends on a local area network, you need to set up this, here it says IPX. You need to set up this IPX. and they do not offer TCP/IP at that time. So, but today, almost every application games you are using, we are using TCP/IP. We are not using other at this level, at the network level and the transport layer. We are not using other protocols anymore. So this has led to something very interesting. So this is called the hourglass internet architecture. So at the network layer, we only have IP protocol. No matter it's IPv4 or IPv6, we are only using IP protocol. And on top of that, we are using TCP and UDP. But above that, the application level, we have HTTP, and on HTTP, we have all kinds of protocols. And all the applications, they can design their own protocol on top of either TCP, UDP, or some of them develop their protocol on top of HTTP. So there are many protocols at the application layer, and also the data link layer. Because we have all kinds of hardware networking devices, and they have to use different protocols. And we are creating a lot of new hardware devices, so we have all kinds of new protocols at this layer. But the interesting part is there is a very narrow waist here. So we only have IP at the network layer and TCP, UDP at the transport layer. So there was a very interesting paper, 2011, like 5 years ago. It was published at ACM SafeCon. This is like the best conference, the most prestigious conference in computer networks. So this paper talks about how we arrived here, why we have this hourglass-shaped architecture, and how will our internet architecture protocol evolve in the future. So I will upload this paper. This is optional. So if you want to get into this, I think this is fun to read. Okay, then we talked about the OSI model. So we want to compare the OSI model with the TCP model. So you may have read this from a lot of places that the TCP model has 4 layers or 5 layers. But actually, if you read the RFC, talking about the TCP suite, you will find out they never officially say how many layers are there. They never say that. They never claim that. But if you understand the protocols, you can easily map those protocols to different layers. For example, we have an application layer like the HTTP, and we have a transport layer. Some papers they call the transport layer host-to-host layer, because it's like you are sending a mail to someone directly. So everything below that will be transparent to you. So it's kind of like host-to-host. And the network layer, some people will call it internet layer. If you say the network layer, it's also fine. And the data link layer, there are many names for it. Some people call it network interface layer. Some people call it network access layer. And some people call it host to network layer, and the physical layer. And if we map this, we map the OSI model to the internet model, or map the internet model, the internet reference model to the OSI model, we can see that the application, presentation, and session, they can be combined and mapped to the new application layer. So imagine that when you are, the previous example, you write a letter and you translate the letter and you create a session to make sure the recipient gets the letter. All those functionalities can be achieved at one layer, application layer. And sometimes maybe you don't need to translate the layer. So we don't really need a presentation layer. That's why all 3 of these, they can be simplified to one. And the transport layer can be directly mapped to the internet reference model transport layer. But like I said before, we're only using two protocols, TCP/IP, TCP/UDP for transportation. There are some helper protocols, but those are the two for actual transport data. And at the network layer, we only have internet layer, or the protocol we have is IPv4, IPv6. And the interesting part is the data link and physical layer. So in this figure, you see those two are combined and mapped to data link layer. But you can find a lot of literatures. They are saying they separate these two. And some of the literatures, they don't even mention this physical layer. For example, this is the book, this is a famous book for textbook for computer networks. So if you are taking computer networks, maybe you are using this book. So in this book, the author used a file layer model for TCP. So the difference is the physical layer. He make the physical layer a separate layer. So sometimes, people find it really confusing. Some document will say, this device works at level 3, this device works at level 2. And it's really confusing because you're not sure which model they're talking about. So you should look for, okay, they're talking about transport layer or network layer. Or they specifically saying, I'm using the OSI model. So why it is confusing here? Why some people want to separate this and some people want to make them consolidate into one layer? That's because the physical layer and the data link layer, they are tightly coupled. So in most cases, they are implemented in hardware, in a network adapter. So sometimes it's not necessary to separate them, but sometimes it would be easier for you to understand if we make their distinction very clear. So before we dive into the physical layer, so today we're going to talk about the physical layer and data link layer. I will just give an overview, and the material I'm going to talk about are related to security problems. So there are a lot of other functions the data link layer will do. Maybe those are its major functions, but I'm not going to cover that in this class. So before we dive into that, let's learn a basic concept called protocol data unit, PDU. So a protocol data unit is the information delivered as a unit among peer entities of networks. So it contains control information, addressing information, and your data. So in a layered system like the OSI model or TCP model, the PDU represents a unit of data specified in the protocol of a given layer. So each protocol at different layer, they have its own PDU, and the size might be different, and the name is even different. At the application layer, a PDU is just called data or message, like the letter you're trying to mail. We treat it as a whole thing. That is the unit we're trying to mail. But at the transport layer, we will segment it. So the PDU is a segment. It's called a TCP segment. And if you are using UDP protocol, it's called a UDP diagram, actually. And at the internet layer, PDU is a packet or a diagram. And I believe packet is the most familiar word here. And in data link layer, the PDU is a frame. So today we're going to talk about this frame. And at the physical layer, the PDU is just a bit. The physical device, it doesn't need to, it receives and it sends. It doesn't need to understand what it is. Everything to it is just zeros or ones. So when you want to send out something, the outgoing data is first packed and identified for delivery to the layer underneath. And if you have an incoming information, that layer, all the layers will try to pass that information, try to pass that data, and decide who do I want to send this data to. And by parsing and packing this PDU at the different layers, actually we are adding control information, sometimes remove control information, and sometimes even modify control information. And most of those control informations we put in a header. Some cases we put in a trailer. And if we put in a header, it is most likely we are giving a source address and the destination address. And the trailer always have a data integrity check for security or reliability reasons. So each layer has its own different header and trailer. We're going to use one example to help you understand how this works. Imagine you are using a browser on your laptop to download a file from a website. So what you can get from this sentence? There is a website, there's a browser, so the application level protocol we are using is HTTP, and it is on TCP, on IP, and the data link layer, it could be on all kinds of things. So what this website, the web server does is it will first retrieve this file from its local storage. We call this just data or message. And the web server will add a HTTP header on this data. And in this case, this will be a HTTP response because you are requesting some data. And then it will add a TCP header. And this whole packet, this whole information is called TCP segment. So the OS will add another IP header. And the network adapter will assume it's a workstation web server. So it is connected to the Ethernet. Then the network adapter will add an Ethernet header. So each layer, the header, it has the source and the destination. At the application layer, the source is like the URL. That's the only one. There is no, yeah. And at the network layer, there will be source port number and destination port number. This is a TCP port number. And at the IP layer, it will have an IP address for destination and for source. And the Ethernet layer, they have the MAC address, source MAC address, and destination MAC address. We will discuss in a moment why do we need address for each layer. And then the network adapter just send it out like this, like zeros and ones. And on your browser, on your laptop, your laptop network adapter detects something. There are messages coming in, and it tries to pass this. And it says Wi-Fi header. So look at here. The interesting part is data link layer header is different. Previously, it was an Ethernet, and now it's a Wi-Fi. And your network adapter at this moment, it doesn't care what this payload is. It just knows, oh, this is a frame, and I want to send it to the upper layer. Then it sends it to the OS, and the OS check, oh, this is a IP header. This is an IP diagram. And it checks the IP header. In IP header, there is a field called protocol, I guess. So that protocol means the upper layer protocol. And that one, for example, here, it specifies this is a TCP segment. So it will send this to the corresponding application that is linked with that TCP port. And in this case, that port is used by this browser. So the browser gets this message, and the browser says, oh, this is a HTTP response. And it will retrieve the data eventually.
Question?
Sure.
Why is it called payload? When it's going from the browser to the computer, it's data, but here it's payload.
It doesn't care where it is.
You mean you're talking about this one or all the payloads?
Well, yeah, just going up it's
Because at each lower layer, it doesn't care what it is. It's just some data, some payload. I don't care what it is. I will just send it out. And this layer will try to pass what it is. So payload is like a very general term here.
I have a question.
Mm-hmm.
So, how big is the all these headers compared to the payload?
Depends. For, actually, we're going to talk about that later. For example, the header is only 20 bytes, but the payload can be, the whole IP diagram can be 64 kilobytes. Yes. But at different layers, there are some limitations. I will talk about that in a moment. So we say that first, the file is, it might be a huge file. So can we really wrap it in one TCP segment? It might be difficult to do that. It will reduce the reliability. And another problem is if you are watching Netflix, you cannot wait for the whole movie to send to you. They have to send you whenever one packet is ready and you can watch the movie. That's called streaming, right? So the transport layer will segment the upper layer data, which, for example, in this case is a file. The transport layer will segment that, split it into smaller pieces. And every time it is split, you need to add a new header, a TCP header. So this one is a TCP segment. This is another TCP segment. And the IP layer, the network layer, do the same thing, but for different reasons. The IP packets, they have to be carried out using the data link frame anyway. So for some physical constraints, a lot of data link layer or physical layer devices, they can only send the frame with a specific size. For example, in the most popular one, the Ethernet, the biggest frame is only 1,500 bytes. So if you have, but the IP packet, the header is 20 bytes, but there is a field called total length that one specifies the total size of the IP packet, and that one I think it's 16 bytes or more. Anyway, it's the size of that field is 16 bytes, and the size for IP packets can be up to 64 kilobytes. So if we want to send the IP packets over Ethernet, we have to split it. And this is called IP fragmentation. It's very similar to TCP segmentation, but the purpose might be different. So the same, after you split the IP packets into smaller pieces, and you need to add an IP header on each fragment. So next, we are going to give an overview of each layer, starting from the data link and the physical layer. And Wednesday, we are going to talk about the network layer and the IP addresses. So today, we're going to talk about the link layer addressing and how hubs and switches work. The data link layer is a protocol layer that transfer data between adjacent network nodes or between nodes on the same local area network. So this is very important. It means the data link frames, that's PDU, right? The frames, they will never cross the boundary of a local network. And all those data link protocols, They only care about deliver data in a local network. What does that mean? In our previous example, this is the message the web server sends out. It sends the data, the HTTP header, the TCP header, the IP header, the Ethernet header, and a trailer here. But this is what your laptop, the Wi-Fi network adapter actually picks up. So first you can notice the difference is the data link layer header. This one is Ethernet, this one is Wi-Fi. Obviously you can understand why they are different because they are different, physically different. But the interesting part is all the other parts, even IP headers, TCP headers, and of course the trailer, they were changed too. So it might be difficult for you to understand why these are changed and easy for you to understand this is changed. So we will talk about this Wednesday. But you can see that this is the actual frame the web server sends out. This frame never get out of the web server's local network. That web server may connect to its own gateway, its own router, and that router somehow sends out the data to our ISP's network, and our ISP sends that to our home Wi-Fi router, and our network adapter picks that up. So the part remains same is the HTTP header and file data. This one remains same at the sender side and also the receiver side, but all other parts are changed. So that is why sometimes maybe the IP headers, TCP headers may not change, but in the example I showed you, the broader one, they do change. So that's why the whole frame never get out of the local network. That's why it says the frame do not cross the boundary of the network. If it wants to cross the boundary, it has to do a lot of changes. So the data link layer is also called the host to network layer, network access layer. I'm not, in the exams, we're not going to ask questions on those things. They're not important. And in different books, different papers, they use different terms. And so this layer is responsible for transferring frames by different protocols over different links. We're familiar with Ethernet, and there might be some different links between routers and routers, and also we're familiar with Wi-Fi. So this is another example, an analogy here. So it's like you are having a trip from Phoenix to San Francisco, and you take a taxi from home to Sky Harbor, and this is a local transportation. It's like the Ethernet. And then you take a plane, and you are the application data. You are the payload in this example. Then the plane will take you from Phoenix to San Francisco. That is like between routers. The router is doing that job. It's intercity transportation. And when you arrive at San Francisco, you may use a different local transportation. In this case, similar to Wi-Fi. You may use a shuttle bus. So, like I said before, the data link layer, did I mention it? Maybe not. So the data link layer is not really part of the TCP IP protocol suite. So the TCP IP protocol suite defines IP, defines TCP, UDP, but it doesn't define what is the underlying protocol. And so most of those data link layer protocols, they are implemented in hardware, like network adapters. So they provide the service for TCP IP. So so the computer can build IP diagrams and and data link layer header to IP packet. So there are three very popular data link layer protocols. The first one is called PPP. It has nothing to do with P2P. So the one you are familiar with, P2P, is actually an application layer protocol. It's not this P2P, PPP. So PPP is a dial-up internet access. So you have a modem like this, you plug in your telephone line, and this modem will decode and encode your IP diagram, your IP package into audio frequency signal. So it will look like this. They will add a PPP header and IP diagram. So why it is called point-to-point? Because when you do a phone call, you are establishing a point-to-point collection. So your modem is establishing a point-to-point collection with some device the ISP has. So you are not sharing this telephoning network with anyone. That's for you at that moment. And another one we're familiar with Ethernet. So Ethernet is a family of protocols that used to build local area networks. So the frame of the Ethernet looks similar. So this is the IP diagram, and we have an Ethernet header and an Ethernet trailer. And we also have Wi-Fi, and Wi-Fi is a technology that enable your mobile devices to connect to a wireless local area network. So the IP diagram part remain the same, only the Wi-Fi headers and Wi-Fi trailer get changed. So the important thing here is if you are on a network, you need some kind of identity so people can find you. Other hosts can find you. And we said before, at a different layer, they all have this identity or address. Why this is very important to security? Because if there is identity, there is identity theft, there is spoofing. So at this data link layer, this address is called MAC address. So the Ethernet and Wi-Fi network adapters, they all have a MAC address. But the PPP protocol, those modems, they don't have a MAC address because they are not really sharing the communication channel. But if you are using Ethernet, you are sharing the communication channel with other devices on the same network. Same as Wi-Fi, you are sharing the radio frequency. So the MAC address is a unique value associated with a network adapter. And sometimes the network adapter, it has a lot of name, network interface controller, or NIC. If you say, you may say this or not in the future, NIC, that means the network adapter. So this MAC address is also known as hardware address or physical address. So if someone asks you what is your physical address of your laptop, they're not talking about where is your laptop located. They're talking about your MAC address. So MAC address, there are 12-digit hex numbers, 48 bits. So last Friday I said it's 64-bit. Actually, it was wrong. It is 48 bits. So usually it is written this way. So each one here is like a hex number. So theoretically, each leak should have its unique address. So how to make that possible? So the first half of the MAC address, the 24 bits, contains the ID of the manufacturer. And the next 24 bits are the device ID assigned by the manufacturer. So if I give you a MAC address like this, by looking at the first 24 bits, you will be able to find out who manufactured this network adapter. In this case, 0080 say 9 is from Intel, and the E0 A6AB is from Apple. So let's see how the Ethernet and the Wi-Fi header, frame header look like. So here is the destination MAC address. This is the source MAC address for Ethernet. And the payload in this case would be the IP packets. And the Wi-Fi would be a little bit more interesting. There is a destination, there is a source, there is also a MAC address for the router, and a MAC address for the access point. And also the payload here. So let's look at two network devices, Ethernet hub and Ethernet switch, how they work. So Ethernet hub is a hardware device to collect multiple hosts together. So to make them act like a single network or network segment. So hub is a very stupid device. It only regenerates the frames and broadcasts them to all the ports. For example, in this case, these 4 computers, they are on the same network. And the workstation A wants to send some information to computer C. What it does is it will send the frame, and the data link layer is a frame. It will send the frame to the hub. And the hub will just make 3 copies of it and send it to all the computers. So the problem is computer B should never get this. What if it contains some sensitive information, like some secret communication between A and C? And it will consume the bandwidth because they are sharing the same communication channel. So hubs, they're not really used right now, but it's good for you to understand all the concepts. So if you build a large network using hub like this, you can imagine there will be a lot of problems. This guy sends a package to this guy, and everyone here will even get the message. So I have a question for you. Which layer does a hub work on? Data link, physical, any other? So this is a little bit tricky. Depends on, because the data link layer is confusing, right? Sometimes it contains a physical layer. Sometimes it's only the data links there. But the accurate answer would be physical layer. Because, why is that? Because the hub, it is not passing anything. It's just a copy and send out. It is not doing any kind of passing interpretation. It doesn't look at the MAC address, the data link layer header. It doesn't do that. So to solve the problem hub has, I think the Cisco, they first invented a switch. So switches will forward frames selectively. It will not forward the frame to all the ports. It will only forward frame to the port that need it. So in any switch, there will be a switch table. Sometimes it has other names. Some people call it a MAC. Some people, it is called a MAC table. So basically what it does, it maps a MAC address to an outgoing interface. And the outgoing interface here is a physical port, not the TCP port, the physical port on a switch. And it is intelligent. It can learn the switch table automatically. How it does that? Whenever a package is received, a frame is received on a port on a switch, and the switch knows, oh, this can associate this port, the physical port, with this MAC address. So it builds knowledge automatically like that. So let's see how it works. In this case, we assume this switch already built this switch table. So port 1 is mapped to this MAC address for machine A, and port 2 mapped to machine B. And when machine A wants to send a frame, it will send it to the switch. And the switch looks up the table. Oh, you want to send it to C, and I will only forward it to this port, not every port. So I guess some of you have experience with a switch. And you may see the computer side, there is a Ethernet port. And on the switch, there is another Ethernet port. So I have a question for you, 2 questions. First, which layer does a switch work on? Yeah, it's the data link layer, because it is looking at the MAC address at least. But actually, this is a very traditional switch. The modern switch are much more intelligent. They can look at the IP headers, TCP headers, and there is a very hot area in networking. It's called software-defined networking, and those switches, they will be able to look at all the fields of your packets. So in the future, the switch, they will not only work on the data link layer, but the traditional switch, the one I'm showing you here, only works on the data link layer. Okay, another question is, here is the Ethernet port. Every computer has an Ethernet port. And also the switch has many. Does the switch has a MAC address there? The port? Each port has a MAC address? No. The traditional one, they don't have to have a MAC address, because they are just doing the forwarding. There is not necessary to have a MAC address here. You are not sending it to it, because there is a direct link there. So that's all for today. So Wednesday, we're going to talk about network layer and how IP addressing works.
Switches ever have an output for that?
So does the switch map MAC addresses to ports?
Yes.
Okay. So if another computer is listening on the same port as the next computer, they could.
If it's Ethernet, they cannot do that.
Oh.
Because that's physically plugged in.
Oh.
Yes, but if you are talking about Wi-Fi,
So they would both receive the frame.
yes.
If they're both listening on the same port.
So in the Wi-Fi case, it's not like listening to that port, because it's like open, right? It's radio frequency.
Okay, thanks.
Sure.
About the switch. So it was something I feel like I learned in 434, but the table was initially empty. It essentially acts as a hub first, right? It would send it to all of the and get the MAC addresses.
Yes, that's how it learns.
So, but initially it would act as a hub.
Yes.
Okay, so in that case, it's that physical or data.
Address resolution protocol happens at the data layer.
He's talking about not ARP. ARP is from MAC to IP. So normally we're not trying to do that.
Yeah, right.
Yes. Yes, but you can.
So yeah, I finished reading the materials you sent me. And yeah, apparently they ran an extensive battery on tests on